This short lecture is about the procedure to construct the element stiffness matrix K of E here with the quadratic basis functions. And this is a standard set of basis functions as the second order polynomials, that is p equals to 2 for the tetrahedral finite element as I sketch here. As you can see, we have 10 functions and each one is associated to the topological entity of this tetrahedron as I label here. So for example, psi1 is for vertex 1, psi2 is for vertex 2, and so on. And with psi5, it is the first edge function, so it goes with edge 1 here until psi10. So this is what we mean by the quadratic tetrahedron. You should know by now, since we have 10 basis functions, we will have 10 by 10 element matrix, and the procedure to compute for the element matrix is very similar to the one we did for the linear tetrahedron. The main difference here is we have to deal with the second order polynomials. Just like we construct the element stiffness matrix with the linear basis functions, we must perform this integration. Remember, this is a volume integral over the tetrahedron domain. And I want to emphasize that we have a choice here. We can use either numerical integration, or in this special case for a tetrahedron, we have the exact integration formula. Here I will show you the procedure with the exact integration. So the first step is to express the gradient of psi for each function. This is what I mean when I say the procedure is the same as for the linear element. We make use of this expression of the gradient of lambda, that is the natural coordinates, in terms of this bi, c of I, and d of I, and they are related to the vertex coordinates of this tetrahedron. The integration is evaluated exactly, and this is the formula for the tetrahedron. You can find this formula in any good FEM book, like this famous Zinkiewicz book. Let's have an example here. We have the first basis function, psi1, 2 lambda 1 square minus lambda 1. To take the gradient of psi1, we want to have the gradient with respect to lambda 1. So we use the chain rule here. It's going to be, so the gradient of psi1 is 4 lambda 1 times grad lambda 1 minus, so this is simply gradient lambda 1, and we have the gradient. Now, the first entry in the element matrix, K of 1, 1, is like this. Here, as before, I use a short form of the integration. This should read, multiply the two terms together, then integrate over this tetrahedron. The first part is squared, and then the gradient of lambda we write as a dot product. And I want to keep this as a dot product. You should see that this is just a constant, so we can take it out of the integral. So as you can see here, this polynomial has 3 terms. We will integrate each of the terms with lambda 1. That is the first 2 terms here separately, and we will use this formula. So you have here lambda I, lambda j, lambda k, and L here as 1, 2, 3, and 4. And the degree for each one is R, S, T, and U. Now if you look at the first term here, 16 lambda 1 square, that means R is 2. The rest, S, T, U, are 0. We're going to have 16 times 2 factorial times 1, since we have 0 factorial for the rest of the degrees there, and then 2 plus 3 factorial. Then for the second term, you have the coefficient 8, and then the degree for lambda 1 is just 1, so we have 1 factorial. and the rest is the same, so you have this second term. For the last term, you just have 1. So integral of 1 over this volume of the tetrahedron just give you the volume itself. We get the final value of 0.6 times the volume of the element. That's how we evaluate the exact integration. Now we just have to evaluate the dot product. The dot product is actually as we did before with the linear element. So we use this expression of grad of lambda I. We just multiply coefficients. So we get 1 over 36 v square. I use a shortcut here, v instead of v of e. We get the final expression of k11. This final expression is exact. It means the error is only from computer precision, but not the integration itself. Now look at the form of the element matrix here. We are done for the first entry. We have 10 by 10, that is 100 entries. So you have to do for all entries. In practice, we don't really compute this by hand, but we will use a symbolic programming software apps like Mathematica or the MATLAB symbolic toolbox to get all these expressions. That's it. Thank you.